our right-handed coordinate system. So today we are discussing about the Wu experiment. The groundbreaking experiment which challenges the fundamental concept of the nuclear physics. That is the parity violation in the weak interaction. The Wu with her teammates studies the beta decay of the cobalt-60 into the nickel-60, and the Wu find out that the parity is violated in the weak interaction. How does it happen? Now we know that in beta decay, the D quark converted into the U quark, that is neutron is converting into the proton. So what does Wu do? Wu take the very low temperature in order to neglect the thermal effects, and he applies the magnetic field to arrange the nucleus spin in a one particular direction. Now we have two scenarios in which the beta decay process can occur. The scenario number one is that the electron that is emitted is in the opposite direction of that of nuclear spin, and the antineutrino is the right-handed in the one scenario. And in the second scenario, the electron is in the same direction as that of the nuclear spin, and there is a left-handed antineutrino. But both the scenarios follow the conservation laws of energy and linear momentum. From the point of view of conservation law, both the scenarios are possible equally. But what we find out? We find out that both the scenarios are not equally observed in nature. The electrons are emitted asymmetrically. We find out the scenario number one in which the electron is emitting in the opposite direction of that of the nuclear spin is more preferable. The universe is more preferable towards the one direction of electron as compared to its another. That is, we always and mostly we observe that the electrons are emitted in the opposite direction of the cobalt-60 nuclear spin, and we observe only the right-handed antineutrinos in the universe. In the universe, we always observe the right-handed antineutrinos and the left-handed neutrinos till now. And the scenario number one is more preferable. There is a asymmetrically emission of the electrons in the opposite of the cobalt-60 nuclear spin. And what does it mean? It means there is the non-equivalence of the left-handed and the right-handed system. That is the consequence of this experiment, that we find out that the parity is getting violated in the weak interaction. During the weak interaction, during the beta decay, the quark changing from D to U, and there is only one preferable direction in which the electron is emitted, and that is the opposite direction. There is no 50-50 probability. There is no equivalence between the two-handedness system, but we find out that there is more priority given to a one scenario rather than the another, even though both the scenarios were allowed by the conservation laws. But even then, because of the parity violation, there is electron always emitted in the one preferred direction as compared to another. There is only one preferred direction as compared to the another direction. What does it mean? It means in weak interaction, in beta decays, the parity is getting violated. And we find out only the right-handed antineutrinos and only the left-handed neutrinos. Clear? And that means the mirror image is not the superposition of its image. And as a consequence of the Wu experiment, a groundbreaking experiment which explains the parity violation in the beta decay, we find out that in the beta detectors, we use the magnetic field, we use the low temperature in order to neglect the thermal effects, in order to perform the experiment in a better way, and as a result of it, we find out that the universe is not symmetric with respect to the parity. There is no equivalence between the two coordinate system. The left-handed coordinate system and the right-handed coordinate system is non-equivalent in the cobalt-60 decay. Clear all of you? So this was the